Try to cover a few different topics that we haven't done yet. There is not enough time to go through everything there is to know about exoplanets in one more class. But I'll try to cover a few of the important concepts at least, if not so much the results, at least the ideas. And I'll try to put a few references also, in most cases, to things that have more information about how they're done and how it works. So if you're interested, you can always look up more information or talk to me. I don't like teaching computer rooms because everyone's behind computers, but let's try anyway. So you have more time after this afternoon to finish all the exercises. So don't worry about them right now, and just try to work on them this afternoon. I guess the best way to learn something is to listen to me now and then doing the exercises in the afternoon. So let's do a quick recap of some of the things we learned in the last 4 lectures. So, different methods, I guess we all know by now. The only direct one is direct imaging, which has a few dozen planets. And then everything else is indirect, so everything else is measuring the star rather than the planet, typically measuring either movement of the star, brightness of the star, in this case also movement of the star in the sky. And then this is, again, brightness of the star due to gravitational lensing. And then there is timing, which I put up on some of the other slides before, which again has something to do with movement of the star, with Doppler shifts or spatial movements which cause a shift in time, like transit timing variations or pulsar, the very first planet. Amplitudes from radial velocities, I think we've gone through it enough, so I don't want to repeat too much of it. So with radial velocities we measure masses, or at least minimum masses, with the unknown inclination. So one of the exercises today or this afternoon is about one of the planets that was in the radial velocity datasets, like dataset 2 from radial velocities, and is also in the transit dataset. So for that one, you can look at the transit, measure the radius of the planet from the transit, and then you will also know sin I, so you can get the true mass, and then you can get the density of that planet and conclude something about its composition. So that's one of the exercises. So if you only look at one of the stars, maybe look at that one, because you can get both mass, true mass, radius, and then density out of it. So eccentric orbits are more complicated because of their shapes. As we saw, they can get quite different depending on where you are. And the steps of going through it, some people did actually implement it pretty good, and otherwise I put online my code where you can see how it's done. In a few lines you can actually generate two-body problem and get your own orbit solution for eccentric orbits. A typical transit, which parameters do we get out of a transit? Let's radius. Yes. True. So planetary radius, if we get radial velocity, we get a true mass. Orbit, so same major axis, you mean? Yeah? The distance from the star to the planet. Temperature, at least, yeah, so at least a theoretical temperature. So based on distance and temperature of the star, you can get a theoretical temperature of the planet. And in some cases, as we'll come back to, you can get an actual idea of the temperature from seeing some of the radiation from the planet. But purely the transit itself gives you ratio of radii was mentioned, same major axis. It's actually radius of the star divided by same major axis or something like that, so it's not directly the same major axis. We're missing a few. What else sets the shape of a transit? The bottom of the transit is not flat, so it gives you... That's right, but that was not my question. Limb darkening, yes. So we get a few different ones. So ratio of radii, impact parameter or inclination, so one or the other, usually, depending on how you want to define it. A value between 0 and 1, or an angle between 90 and wherever you are. And then R star over A, so the same major axis if you know the radius of the star. And either you can also convert this into a stellar density, so you get an idea of the density of the star. And then limb darkening, the shape of the bottom of the transit. So in one of the bonus exercises, you can play around with an actual transit model. So that would be this transit model. So this is the analytical model implemented in Python for you in the code that I was like linking to in the exercises. And then you could, if you use that, you could choose your own ratio of radii, inclinations, R-star array, and limb darkening values, and generate an actual transit from that, and compare that to the actual data. So you could, for example, try to estimate this one already, or these values a little bit, and see how that works, or try to play around with them and change them a little bit and see how that changes the transit. So what you should be seeing roughly is, if you change this one, you change the depth. If you change this one, you change the shape, like V shapes versus flat shapes. If you change this one, you change the total duration. And if you change the limb darkening, you change the shape of the bottom of the transit. So that's roughly how things change, but all of them are correlated, so they will always do more than one thing. False positives. What kind of false positives are there? Two categories. Instruments. And yeah, and astrophysical, I want to say, so real, like real events that are not instruments. So I've mostly ignored the instrumental effects here. They are real in some cases and they can be really annoying, but typically they're easier to understand. It's easier to distinguish between something about your instrument and planets. It's not always true. You can have really small planets where it's really hard to see if things are real. But these ones are much more of a real concern because they can look really very much the same. You can really have eclipsing binaries in the background that in total look like a transit that looks exactly like a planet. So there's absolutely no way to distinguish. So even taking just, even if the signal is really good and there is really little noise, you would still not be able to just distinguish without getting additional information because they would look exactly the same. Whereas with the instrument things, usually you could take more data of the same instrument and most noise will not follow exactly like a transit. So usually you'll see things go away once you get more data. Yes?
Even if we do like the statistics that you mentioned, it could actually look exactly the same as a planet?
Yes. So an eclipsing binary, for example, the geometry of this, like of an eclipsing binary in principle, is the same. I mean, the physical effect, what's happening is exactly the same thing. It's two bodies eclipsing each other. So, things will still depend on ratio of radii, on inclinations, and so on. The only real difference is normally an eclipsing binary is bigger, like the binary is bigger than a planet would be. So you can get different depths. And in practice, you could get different shapes depending on the properties. But, in principle, there doesn't have to be any difference at all. Like they're just two bodies eclipsing each other. So the physics of a binary star eclipsing each other, like most of its geometry is exactly the same as for planet transits. And so if you dilute things enough with another star and you get the depth to look different, you can literally have the exact same shapes.
I understand that, but you mentioned some statistical analysis that you make to see if it was one or another.
Yes.
So what would that analysis?
Well, so what you can do is you can try, it's okay. So the two different ways of ruling it out, let's just put them up both. So one is radial velocities, in which case you're pretty safe because you found the planet in a second way, so then you're fine. The statistical analysis will typically rely on making one scenario much less likely than the other. So that can work. But typically this doesn't work on its own. What you would, for example, do is you would take images, like high resolution images, to see if there's any other stars nearby. Like that will give you additional information. If there's no other stars nearby, it's much less likely that there will be some kind of binary somewhere. If there's no star at all, there can be no binary. So that's additional information that would help you distinguish. But just from getting more transit photometry, more Kepler data, you won't really gain much more. The statistical analysis typically does not rely on just looking at only the photometry. It relies on combining that with different data sets, like high resolution images, maybe some radial velocities, even if you can't see the planet there, maybe you can still use it to rule out some other scenarios. You can take a new transit, but in a different color. That would help you as well. That's what we saw. Take a Spitzer image or an infrared image. But that's all adding new data, like different sets of data, rather than just having, higher signal to noise. The instrumental stuff, you could typically, at least in theory, just get more of the same data. Eventually, hopefully, the signal will get higher and the noise will get lower, and you will see what's happening. That will not work for these kind of things, because the signal to noise is not the problem. It's distinguishing between two things that look the same. Okay, so different ways of finding planets. Yes?
What do we get like the same phenomenon in the graphic? In the graph, when we see a transit between a binary star, if the smallest star is actually brighter too.
Yeah. So, okay. So maybe I should. So it is possible that binary stars, for example, will have a different eclipse. So I said that the geometry is the same. Now that's only strictly true for like a dark star, because when we measure eclipses the way we do it now, we assume the planet's completely dark and the star is bright. When we have a binary star, that's typically not true. Like both stars shine, so that can give you a different eclipse. Like in a planet, if the planet would have been the exact same size as the star, you would get a total eclipse, like 100%. In a binary, you would get 50% if they were equal brightness, right? Because one of them would still be shining. So you do have, in principle, some differences. Also, if you have really close in binaries, they will interact with each other, and so you will see different kind of eclipses. Binaries will often have two eclipses, like a primary eclipse and a secondary eclipse. So you can sometimes distinguish based on what things could be. But it depends on the binary. So you can often rule out certain types of binaries by looking and saying, well, this kind of binary, if it was a really close in binary, it would look different than what we're seeing. But still, even that would be statistical analysis. You would be trying to say, these kind of binaries are impossible. Only this specific type of binary is still possible. There's only so many stars in the sky, so it's very unlikely, something like that. Okay? So, then yesterday, no, that's wrong. Friday, we talked about a few of the results that we got from transits. So we went specifically, we talked a bit about TRAPPIST with a question about why going to small stars is useful. Anyone?
Because you can get, you got a bigger planet, you can get more, you can get a bigger transit.
You can get deeper transits because the stars are smaller. Yeah, that's the main reason. So if you compare the stars, stars so small, the transit will get deeper. There's other reasons though. Anyone? Any other reason why maybe we were interested in going to smaller stars? We didn't talk about it that much Friday, but one option. In principle, yes. So in principle, smaller stars are also less massive, so they'll move more, and so rate velocities would be easier. But in practice, it doesn't quite work that well because the smaller stars will also be a lot less bright, and so it's also a lot harder to do rate velocities in that way. So if only getting like rate velocity precision was the goal, small stars are not necessarily the solution. But there's another reason. Why do we want planets around small stars? Think.
Because planets will have shorter periods.
Planets could have, yeah, you're on the right track. Planets could still have any period, but
There will be more planets close to the star.
maybe. Right. It's easier to detect planets that it might be in the habitable zone. So, regardless of where the planets are, it's always easier to find short period planets than long period planets for a range of reasons, like the fact that they transit more likely. Long period it's very unlikely to transit, but also just if they're short periods, they will transit more often. So it's a lot easier. Like with 1 year of data, you could get maybe 50 transits if it's only a period of 1 week, or if it's a period of 1 year, you could only get 1 transit. And to get 50, you have to wait 50 years, which is, beyond what most people are prepared to wait for. So it's easier to find short period planets, and around small stars, the short period planets will have lower temperatures because the stars are less bright, shine less. So the planets, a 10-day period planet around a star like TRAPPIST-1, with the planet a period of 10 days, it will be fairly cool planet, whereas a 10-day period planet around a star like the Sun will be very hot because it receives a lot more light. So if we're interested in those planets that are somewhere, possibly have liquid water, for example, that are not too hot, it's easier to find those here than it would be to find them around the Sun. Because around the Sun you would need to go to like the Earth, something like the Earth, so 1-year periods. For small stars you can go to, for example, 10-day periods, depending on the star. And in addition, once you found them, it's also a lot easier from a practical point of view to learn more about them, because they will transit more regularly. It's a lot easier to schedule some observations if the transit happens every 10 days than if it happens only once a year, when you have to wait for it. And if you happen to miss it, or it happens to be, I don't know, bad weather in your telescope, you'll need to wait another year, which can be really really annoying. So short period planets have their advantages from a practical point of view, and they will be cooler. So that's another reason to go to the small stars.
I got another question. Can we get actually the rotational period of the planet with transit data, or also combine it with other methods data? Can get the rotational period?
Okay, so the question, like the rotation of the planet, so you mean rotation around its own axis, like the 1-day thing for Earth? In principle, no. Like in most cases, the answer is definitely no. Like in principle, the fact that the planet's rotating during a transit will not influence the transit in any way. So normally, no. We have rough ideas that the close-in planets are tidally locked, so you'll always see the star. They have a day side and a night side, like the moon. We always see the same side of the moon. So that's a theoretical idea more than a practical measurement. There is some ideas for really close-in planets that are maybe not completely spherical, like they may be misaligned slightly. They may, in that case, you may be able to get some idea from the shape of the transit. But in practice, no, we don't know from transits. There is one measurement for direct imaging from Beta Pictoris, where we're actually seeing the light from the planet, right? We have an image, so we see the light from the planet, and there you can use the width of the lines of the planet to get some idea. Now this is very hard to do, and so that's one rotation measurement that we have. But normally, no.
Like something like analog to how we get the rotational period of a galaxy, then we see the Doppler shift. If it's going something like that. I know it's too small, but if you get like with a coronagraph to block the...
Yeah, but so in principle, for most transiting planets, we don't see the planet at all. So we don't see any light from the planet, so we can't measure the lines, so we can't.
No, I mean for any other method.
Yeah, so for that, there is some ideas that for example, radio velocity planets, if you somehow manage to detect actual light from the planet, you would be able to do these kind of things. But in most cases, all we really see is a star and nothing else about the planet. And so that doesn't work. Okay, so that was going to the smaller stars for multiple reasons. So the very obvious one is the depth. So here you have depth, they're more than a percentage deep, which if this was around the Sun, this would be a Jupiter-sized planet. But because this is around a small star, these are planets that are the size of the Earth. So it's a lot easier to find small planets. And then we also talked a bit about transit timing variations. So the gravitational influence of planets on each other, as well as on the star, will cause transits to not be strictly periodic. So if there's only one planet in a perfect two-body problem, you will have a transit exactly one period later. If you have multiple planets that influence the star, you will not necessarily have a transit exactly where you expect it. It may be slightly early or slightly late in time. And so that's what you see here. Like the 0 point is where you would expect the transit to be every one period. And you can see that some of them are slightly late or slightly early. Probably the most obvious here, but you can really see there is a difference in when the transit happens. which is caused by the fact that the star is also moving as the planets are transiting because of all the other planets. Okay? And so this can be used for two important things. Why do we like transit timing variations, or what can we use them for? Knowing, so that's one. Finding additional planets. Calculating their masses, exactly. So again, because this is a dynamical effect, because you have different planets influencing the gravity, so this is a gravitational effect, so influencing the movement of the star. In principle, you can understand that you could use this to get masses of all the objects. In practice, it's not necessarily easy, so most of the time people do simulations of different planets with different masses in different orbits, where they would then see if they can reproduce where the planets are at which time and which transit would occur to see if they can derive masses. Not always easy in practice, but it can be done, it has been done, to get masses. So yeah, that's one of the real advantages of TTVs, of transit timing variations. They can give you masses, but in addition, they can sometimes be used to find additional non-transiting planets. Even if a planet doesn't transit, it may still influence the other planetary transit. So you may find non-transiting planets. So yeah, that's the two reasons for doing TTVs. Then, beyond a lot of the measurements from ground-based telescopes, there's also a real push, or a lot of planets found from space-based data. Why do we like going to space beyond just measuring transit from Earth? Also, there's more than one reason here. Why? Precision of the data. That's one. Why? You can get data in data. Why would we go to space instead of measuring transit from ground? So, yeah, precision is an important one, and the other one is mostly continuous observations. So you don't have to worry about the sun, mostly. So you can make measurements day and night, which can be really helpful. And it's of course a lot beyond that, because mostly even from ground, even if you don't have day and night, you lose a lot of time because of weather, because of other people wanting to use instruments. And so it's a lot harder to have continuous coverage of anything from ground. There's a third one, that is that if you want to make measurements in different wavelengths, some wavelengths cannot be done from ground. So in principle also, that may be a reason to go to space, because you can measure things in, you have more access to the whole wavelength range, whereas from ground you're blocked by the atmosphere. So that's the three reasons. Precision is definitely one of the most important ones. We can only really do the small transits from space. If you go to much less than 1%, it's hard to do from ground because of our own atmosphere, just kind of putting a kind of lower limit on how well we can measure any transit of a star, because it's really hard to accurately get brightnesses of stars, because the light has to go through our own atmosphere and gets dispersed, which makes it really hard. From space, we don't have that problem, and we can find much smaller transits. All right. And then I think finally, or mostly, by the end of last lecture, we also talked a bit about occurrences. So to summarize at least the concept again, a lot of it has been done from different surveys and different methods and different data analysis ways. But crucial for all of them is to find out not only how many planets we find, but also how many planets we don't find. And obviously there's another component, which is how many things are false positives. So typically we'll need to do a survey, which will mean counting, how many stars are we observing, how many transits do we find, what kind of periods do they have, what kind of radii, and so on. But that's only one part. Then we have to correct for either some of them are false positives, or we somehow know, which ones are not, or something like that. But also, how many have we not seen, how many have we missed? We're way more likely to miss small planets than large planets, so we'll have to make some kind of corrections for that. One way is to inject artificial transits into the data and then see if our algorithm can blindly get them back. And in some cases that may just depend on the star or on some kind of luck or noise, so sometimes you get back some. So for example, this is just one of the different surveys. This is what you can see here. So here in gray is the raw occurrence, whereas in red is the correction for missed planets. And so you can see that if you go to the big planets here, so this is 8 to 10 Earth radii, this is Jupiter radii, you don't really correct for anything because you find everything. If you go to the small planets, we have much larger corrections because there it's way more likely that we're missing actual transits because they're much shallower and they're harder to see. And so key result which keeps coming back is that small planets are the most common results, much more common than if you go to see like large planets. So they're easier to find, but they're not the most common type of planet. Which is perhaps encouraging for us. Small planets are like Earth, are nice. Big planets are mostly balls of gas. So in some ways less interesting, depending on your preferences, but at least encouraging to see there's a lot of planets like the Earth at different periods. And so we can use those to begin learn about occurrences. It doesn't quite matter, the exact numbers don't quite matter too much. Different surveys will give you different numbers, but generally we find, pretty high numbers, order 10% for different bins or something like that. Some surveys find at least every star should have at least one planet somewhere, things like that. So if someone asks how many stars have a planet, the answer is probably more or less all of them, at least as far as we can tell. Keep in mind this is only for specific stars. It's F and G stars, so it's not for every star. So maybe, it's a whole different question if you wonder if does a white dwarf still have a planet? I don't know. But generally, if you just take the whole universe, a lot of stars have planets. Many of them probably much more than one. Okay. And then really the final point of last lecture was about knowing properties of planets only as good as you know the properties of the star. So to get information on planets, you do need to know stars first. And I put up this question last time as well. Which methods do we have to know things about stars? Spectroscopy. There's very general ones like spectroscopy. Sorry? Astroseismology, good one. So oscillations of stars, so movement of surface of stars, which can be measured, especially actually with Kepler. A lot of them can be measured directly with Kepler because a lot of the movements of the stars will cause brightness variations as well. And so you can measure the brightness variations, infer how the star's surface is moving, and that will give you information on, for example, the density, which will highly affect how sound waves essentially can travel through the star. So you can get things directly from Kepler sometimes. Spectroscopy is another very general method. Then there are very specific ones which only apply to a few stars, not necessarily those with planets. Yeah, that's definitely true. Was not on my list here though. But yes, you can measure things for very specific stars if you know distances. Should have probably put that because that was not here very clearly either. But so one other way to know a lot about stars is if you know the true distance. So for example, if you know the parallax really nearby stars, you can get a lot better information because you know how far they are, which will give you information on how truly bright they are, not just how bright they look like, which will help a lot in understanding their properties. So for nearby stars also we can do interferometry in some cases, actually measuring the actual size of stars in some cases, or at least getting distances right. So that works for nearby stars. But what I meant is, for example, eclipsing binaries, where the eclipses directly will give you properties. In this case, for binaries, you don't just see one of the stars, you see both, not like planets. Where planets you only measure the signal from one star and not the planet. But in binary stars, you usually get both stars. So you can learn a lot about those kind of systems as well. So in a lot of ways, the most general one is multicolor photometry. So just measuring the brightness of a star in a few different wavelengths, where you can then fit a black body to it, and that will give you some idea also of the temperature. That's very general, but the advantage is you don't need much data for it, so it's easy to do if you have no information. Spectroscopy typically requires at least a good spectrum for a star, which is not always available. And then the more specific ways, so clusters, binaries, astroseismology, and yeah, I should probably really add like Gaia here, like the distance measurements that we will get, and to some degree already have for nearby stars. But generally, often none of this is available except for the first two, which may mean If you don't have much, you can maybe not know the radius of the star to more than 50%, which is a pretty big error bar, which will translate completely in how well you know the planet. And so as an example of that, some very recent work that I showed came out just some weeks ago, which was analyzing some Kepler planets. Originally, this is from just multicolor, so pretty high error bars on the star, and therefore pretty high error bars on the planets, where these were all discovered planets. And then if we have better spectra and better information on the star, things look like this, with a much smaller error bar on the star. And you can start seeing a different pattern where it seems like planets here start disappearing comparing to the previous one where you don't see that. So they are the same kind of planets. The real difference is just here. We don't know the star much, and so we are often wrong on where the planet's real size is. And here we're more accurate on where the planet's real size is, and so you start seeing more patterns. So knowing stars is important for many other reasons, but this is just one example. Don't know much about planets if you don't know stars. This is, of course, true for other methods as well. Radial velocities, again, you do need to know stars to know planets. Okay. So, new topics. Maybe let me ask again, what can we use transits for? And now we're going to try to cover everything we haven't talked about before. So, we measured detection, and related to detection, occurrences of planets, right? So we cannot just detect one of them, but we can detect the actual rate of occurrence of planets on different stars, different periods, and get an idea of how many there are. What else can we use transits for? Yeah? What kind of? Radius, temperature, and so on. Yeah? Hold on. One at a time. Composition, yeah. That was hopefully my next one, yeah? So composition. So if we get masses from radial velocities, that will give us densities of the planets, which will give us composition, so that will give us an idea not just of what the planets are like in size and so on, but also what material they're made of. I want to talk about this briefly just next. Other things we talked about, other things for transits beyond mass radius measurements. Temperatures, so phase curves, so we can get secondary eclipses. We can somehow measure reflection sometimes from that. We'll also talk about that today. Anything else? Atmospheres, something we can learn about atmospheres. Yeah, so we can do spectroscopy during a transit, where some of the light will go through the planet's atmosphere and pick up features from the atmosphere, giving us information on the star. On the planet, not just the star. A whole big field on its own, with a lot of complicated work, both on theory and on data. So we'll not have much time to talk about it much. I'll try to give the basic concepts of how this works, but yeah, we need a whole class on just that to really understand this, because this is combining a lot of different tools, and also a lot of knowledge on atmospheres is very hard, because atmospheres are difficult to understand. So okay, so that's the most of the three things I want to talk about today. So so I think some of them we mentioned. Detection have been done, occurrences have been done. We've talked about transit timing variations already. So I want to talk briefly about density measurements and what we've learned, and then I want to talk about the phase curves and how they give reflections and temperatures, and about the transmission spectroscopy, so atmosphere work directly. And then one other thing I do want to mention at least is measurements of dynamics and what we can learn about architectures of planetary systems. How do planetary systems look like, multi, singles? Do they form like the solar system, or do they form in different ways? And what does that tell us also about the solar system? So I know this will be brief, there's different topics to cover, and not everything about every topic, but I will try at least to give you sort of the overview of how things work and what can be done. And maybe one or two big results from each of these different things. And I'll try to give you references for more that you want to know. So yeah, to conclude here also, you do need to, often transits don't give everything, especially if you don't know the star. So let's start with transits and radial velocities and combining them. So I think we've mentioned this already. It's powerful for two reasons. So most of the time people do figure out one. So one is to break the mass degeneracy, right? You can go from m times sinus of the inclination to true m, from minimum masses to actual masses, because from the transit you know it's close to 90 degrees in orbit. It's really important, so you get a true mass, but also combining it with the radius gives you the mean density, the bulk density of the planet, which you can compare to a model to tell you something about where the planet is. Like what it looked like, what material is it? Is it rock, or is it water, or is it gas, for example? Challenges? Anyone? Why is this not always easy, or what are the things we have to do or overcome to make these kind of measurements? Instruments? Yeah. So let's say I have a transiting planet, like I have one with Kepler, a nice transiting planet. Can I get the mass directly from rate of velocity, or like will I generally just get the mass, or is this hard? Depends on where the planet is, yeah. So you're saying depends on the size, or the period, or the place in the sky? First two? Yeah. So definitely one of the big challenges is that in many cases it's just really hard to do, because we are better with the transit method than with the RV method today. So we can do smaller planets with transits than we can with RV. So in that case we can't combine the two things. Also, just generally, even if we can, it's just very expensive to do RV follow-up. Usually RV follow-up means you need a telescope to look at that planet, that star, more than once for sure, often quite regularly over quite a bit of time to get a full radial velocity curve. So you do need quite a bit of access to a telescope to do that. You can't just do it, once. So you'll need, it's quite expensive in terms of telescope time to do this follow-up, especially if you say I want to get masses and for like 100 different planets. That would take a lot of time on telescopes to do. So that's challenges. In terms of Kepler, which has provided us the main planet survey that we want to use probably, because it's a lot of radii. The problem is a lot of Kepler stars are very faint. This is by nature of Kepler. Kepler has been looking mostly at one field in the sky. So if you look at one field in the sky, you get faint stars, because bright stars are all close to each other, close to us. So, if you want to have only the bright stars, you need to look everywhere in the sky, because there's only so many. In the Kepler field, you look at one field of the sky, so mostly things are going to be fairly far away. There's going to be a few bright stars, but if you really want to catch the bright stars, you would need to look everywhere. So Kepler has not done that, for good reasons. We wanted to find long period planets with several years, looking in one field. But it means you don't have many bright stars, which makes it hard. And then also, often people have done inhomogeneous studies. So people have made radial velocity measurements for one planet, but not for a whole big sample, which is not always helpful. You want to do these mass radius comparisons because, maybe their data was enough to be sure it's a planet, but not enough to be sure of the real mass. Maybe they didn't take into account that there could be a second planet that may influence things, so it can be really hard to interpret data from a lot of different papers and a lot of different work with different qualities, different analysis methods, and so on. The other one, this is less obvious, but transit work mostly gives you planets at short periods. By nature of transits, if we have a transit survey, the probability is low at long periods. So mostly, if you have transiting planets, they're at short periods. 10 days, 20 days, 30 days. Very few at 1 year, 2 years, and so on. This is important to take into account because when we're now measuring masses and radii, this may actually depend on period. It may well be that if you get planets closer into their star, they're not necessarily the same kind of planets as planets further out. So whenever we do this kind of analysis today, it's mostly those planets that are much less than 1 AU, and it doesn't necessarily give us information on planets that are further away because they may well be different. They may receive less radiation, they may be different in their formation, so they don't have to be the same kind of planets. So that's also a limitation to keep into account. I do want to add, at longer periods, transit timing variations can sometimes rescue us. if there is planets there, they're hard to measure radial velocities for and so on, but timing variations may, in some cases, give us masses. They don't have so much of the limitation of caring about, we don't need a lot of telescope time and so on. And I want to explicitly mention there's no real agreement between the masses from transit timing variations and from radial velocities, which is a bit of an open question sometimes. People have argued maybe transit timing variation derived masses are not always correct, but maybe more likely seems that perhaps the density of planet at longer periods where you have mostly TTV measurements and at shorter periods where you have mostly RV measurements are just different. So the planets are just different depending on where you are. Okay, so I just want to show you, this is the basic of the concept of measuring densities. I just want to show you a few of the big results that we've learned. I want to show you this one survey by Jeff Marcy, who, again, California survey at Keck. They've done a pretty big homogeneous study of Kepler systems. So they pre-selected, we're going to only look at these stars, and we're going to do all of our analysis in the exact same way. So they had a very big program with dozens and dozens of nights of observations to try to get an answer for a whole sample. And so they had a lot of these measurements. So you can see this for just one of the systems here. But you can see this is data over several years' time, radial velocities. These were the transits. There was 2 planets in this system. And then they get an RV curve for both, which they can use to derive a mass. And you can see, it's a clear measurement, but it's not, a great perfect mass. There'll be a pretty big error bar on these things because it's just still very hard to do. This is just one of the samples. So they have a whole sample of a few dozen of such systems. Just to show you another one, so this is another case where again they have some RV points spread over a few years of time. They have a transiting planet here with the RV curve, another smaller transiting planet here, again with the RV curve. Here it's much less clear if they actually know the mass because it's very small. And then they have one that doesn't transit, but they find pretty clearly an RV trend at a longer period. So this also can be used to discover more planets in the same systems where this third planet seems to be clearly there from the radial velocities, but does not transit. So again, this is why it's so complicated to do this work, because sometimes, if you don't try to find this one, you would only fit for these, maybe you get the wrong masses. So, you really have to take into account all possible additional sources of information or uncertainty. And final point of their study, which tends to confuse everyone, is they did allow for what they call negative masses, which is a really unfortunate naming because obviously actual masses are not negative. But what they really mean is negative amplitudes of their RV curves. Because they know the period and they know there has to be a planet. In some cases, for small planets, rather than having like about a 1 sigma measurement, just because of noise, you're going to have a minus 1 sigma measurement, right? So if you have not so great data, but you know which period to look at, ideally you're going to start seeing a small mass, and then maybe you find a mass of 1 Earth mass plus minus 1 Earth mass, so that would be consistent with 0. For example, that could happen. If you have only a few data points, that could happen. But it could be worse. You could actually find that the mass could be like minus 0.5 plus minus 2 Earth masses. Just because of noise, things are going to peak in different places and sometimes in a negative amplitude. Okay? Does that make sense? Now, there's different ways to deal with this. You can say, well, we know it's not negative, so it has to be at least 0, which is the truth. And then you can give some kind of upper limit, like it can be higher than 10 Earth masses or something like that. But they explicitly chose not to do that, and so they have a bunch of things which are somewhere here, which are actually negative. The reason they do that is because they don't want to bias the results. They say, well, if we remove those, we're going to keep those where, because of noise, we happen to be on the good side, but not those where, because of noise, we're going to be on the bad side. And so they want to take into account everything, so that at least on average, they will get the right result. Okay? But you can see a lot of these error bars are pretty large, and some of them cross 0. It's really just pretty hard to do this kind of work for small planets. And these are the orbital periods, so you see the same thing here. You go to 50 days, that's the limit of their survey, and a lot of them are even below 20 days, so really close in systems, because they're the ones that we can do. And then some of the results of this kind of work, I think I want to just essentially highlight one of the big thing that people have been finding like multiple groups have been finding in different analysis methods, is something like this. I'll highlight it here. So if you look at the small radii, so we're below 4 Earth radii, so things are pretty small. We're finding a kind of cutoff or difference at around 1.5, 1.6 Earth radii, where the general consensus seems to be now that if you go below about 1.6 Earth radii, you have mostly rocky planets, so fairly high densities, you know, things like rock. If you go higher, you seem to find things that are mostly lower densities, so more like gas planets or at least bigger atmospheres, lower densities. So that's not super clear from this plot perhaps. You can see these are gray data points with masses from RVs. There's TTV masses in yellow. The blue points are very convincing, but they're the solar system, so you know, you may want to not include those if you want to say, well, how do we know that's the same? But anyway, this kind of peak, I'll show you in a moment, has been reproduced in other ways as well, finding that, you know, things below about 1.5 seem to mostly behave like Earth, pretty much like a rock with a small atmosphere. If you go higher, you get much bigger atmospheres, lower average densities. So this shows the same thing, but mass versus radius. But let me show it to you in a different way. So this is another type of analysis using a lot of the same data points that I showed you earlier. So the Marcy-Kepler analysis. So they have these